This video is to look at the second derivative test to see what it says and what it does. So imagine that you have f of x as some function and f prime of c equals 0. So c is an x value and the derivative at c is 0. Now notice it doesn't say 0 or undefined, it's 0. Now if it said 0 or undefined, we could just say, hey, c is some critical number, any critical number, but that's not how this is going to work, because we need the second derivative to actually exist on the open interval containing c. So it has to be differentiable, so you need a nice smooth curve going on right there. So we can't have a cusp, but we can certainly have a flat spot. So it has to be a critical number, but not a cusp. So our first derivative at the value is 0 and the second derivative exists. It says if the second derivative is greater than 0, then we know something. So what's going on here is that c, our first derivative is 0. So basically, here's your point, and if your first derivative is 0, then I know that the slope of the tangent line is going to be 0, so my graph flattens out. And then it tells me the second derivative is greater than 0, so it's flattening out, but my function has to be concave up. Well, that would mean it looks something like this. If that's true, then I would say f of c is a relative min. Or I could say there is a min at x equals c. If f double prime of c is less than 0, then we're talking that we're saying at that flat spot, it's concave down. So f of c is a relative max. Or we could say, rather, there is a max at x equals c. Now, if the second derivative equals 0, then I have absolutely no idea. And it's not to say that there isn't a max or a min. There could be. If you have something like y equals x to the fourth, the second derivative is going to be 0, and it's a min. If I have a negative x to the fourth, the second derivative is going to be 0, and it's going to be a max. Or it could just be a point of inflection, and it's neither a min nor a max. For example, at y equals x cubed. So that's the big I don't know case, which doesn't mean you're done with the problem. Generally, it means you have to go back and actually find your mins and maxes another way, like the first derivative test. So a quick example of what this looks like is you start with this function f of x. Now, the first thing I'm going to do is take the derivative. So imagine that your second derivative test failed. You haven't wasted time for long parts of this problem because the steps are the same. So f prime of x equals negative 15 x to the fourth plus 15 x squared. I'm still going to set that equal to 0 whether I'm doing the first derivative test or the second, because I need to find the critical points. It's not undefined anywhere, but I really wouldn't care if it was. If I was trying to use the second derivative test anyway, I'd probably just cry uncle and go back to the first. But I'm going to factor this out. I'm going to pull out a negative 15x squared, common factor, and I am left with an x squared minus 1. So if I set my factors equal to 0, I know x equals 0 is a critical number, and then x squared minus 1 factors into an x plus 1 times x minus 1. So I have three critical numbers, 0, negative 1, and 1. I would have to do that whether I was doing the first derivative test or the second. But I'm going to do the second, so now I go to my second derivative. So I'm going to use the power rule again, multiply down and subtract 1. So negative 60 x to the third plus 30x. Now, I don't have to set this equal to 0, and I don't have to write intervals. That's the beauty of the second derivative test. What I need to know is, what is f double prime of negative 1? What is f double prime of 0? And what is f double prime of 1? If I get something that's not equal to 0 for these, I'm happy, and I know whether it's a max or a min right away, because the first derivative is 0 for all three. So if I plug in negative 1, and negative 1 cubed is negative 1 times negative 60 is a positive 60 minus 30 equals 30, which all I really care about is that it's greater than 0. If I plug in 0, I'm very sad because that equals 0, so the test fails. So right now I'm not going to know if that's a max or a min. If I plug in 1, I get a negative 60 plus 30. And I get that that is equal to negative 30, which is less than 0. So at 0, I have to go back and do the first derivative test, so I'm going to actually be plugging things into the first derivative, which I'm not going to do right here because the point is the second derivative, but more work to be done right there. Okay, imagine that these were my only two critical values. I already know what's going on. For both of these, the slope was flat. For this one, the second derivative was greater than 0, so my function was concave up. So I have a min. For this one, it's flattened out, the graph flattened out there, the slope was 0, but my function's concave down, so I have a max. If I wanted to justify it, I could say f of x has a, we'll do the min at x equals negative 1. Now I know that because f prime of negative 1 equals 0, which means that it is a critical number, and f double prime of negative 1 is greater than 0. That would be enough. Now, on your first derivative test, you talk about the first derivative changing signs from positive to negative or negative to positive. For the second derivative test, you have to include both conditions, that it's actually a critical number and that it's concave up at that critical number. So I'm going to say f of x has a max, a relative max, however you're required to say it, at x equals 1, and I know that because f prime of 1 equals 0, so 1 is a critical number, and f double prime of 1 is less than 0, so it is concave down. And again, you would have more work to do to go figure this one out.